Okay, let's dive right into this explainer. Imagine you're faced with a quadratic equation, something that models a real-world parabolic curve. But no matter how hard you try, it just won't factor cleanly. You're basically stuck staring at numbers that absolutely refuse to cooperate. Well, today, we're going to fix that. We're building the advanced mathematical tools you need to break through those stubborn problems. We're looking at two highly powerful algebraic methods for solving quadratic equations that cannot easily be factored.
Here's our roadmap for today. We'll start with completing the square, move on to the quadratic formula, then see how the discriminant tells all. After that, we'll focus on checking our solutions and finally wrap up with which method is best.
Section 1. Completing the square, finding the perfect fit.
This method is just a completely logical progression of algebra. The core concept here relies heavily on the golden rule of equations. Whatever you do to one side, you absolutely must do to the other to preserve mathematical equality. Let's walk through this step by step, using the equation x squared minus 6x minus 7 equals 0. So, step 1, we isolate the constant by adding 7 to both sides, which maintains our equality and gives us x squared minus 6x equals 7. Now step 2 is where the magic really happens. We take our b term, which is negative 6, divide it by 2 to get negative 3, and then square it to get 9. We add that 9 to both sides. Notice how x squared minus 6x plus 9 equals 16 keeps our equation perfectly balanced. Moving to step 3, we factor the left side into a perfect square binomial, which gives us x minus 3 squared equals 16. In step 4, we take the square root of both sides, resulting in x minus 3 equals plus or minus 4. Finally, step 5, we solve for x by adding 3 to both sides, giving us our two solutions, x equals 7 or x equals negative 1.
Okay, misconception alert. I see this literally all the time. You must never drop the plus or minus symbol when taking a square root during these steps. If you take the square root of 16 and only write down the positive 4, you are instantly losing half of your valid solutions. The math demands that we account for both the positive and negative roots to find all the exact places our parabola crosses that x-axis.
Let's make sure this is clicking for you. I want you to pause the explainer right now and quickly test your active recall. If we're looking at the equation open parentheses x minus 3 close parentheses squared equals 16, what is the very next algebraic step?
All right, we're back. The correct next step is to take the square root of both sides. This results in x minus 3 equals plus or minus 4. Really great job if you remembered the reasoning here. We apply the square root property to isolate x while strictly retaining both the positive and negative roots. Doing this means you're keeping your equations accurate and precise.
Let's jump to section 2, the quadratic formula, the universal shortcut.
You know what's truly fascinating? If you take the standard quadratic equation, ax squared plus bx plus c equals 0, and you complete the square on it using just the letters, you naturally derive this exact formula. The quadratic formula is basically your master key. X equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. It's used to solve any quadratic equation written in standard form. But look closely at that condition at the end, where a does not equal 0. Why is that absolutely crucial? Well, if a were 0, we'd be dividing by 0 in our denominator, which totally breaks mathematics. Plus, if a is 0, it isn't even a quadratic equation anymore, it just becomes a linear one.
Let's put this universal shortcut to work on a brand new example. Step 1. We have the equation 2x squared minus 4x minus 6 equals 0. We identify our coefficients, a equals 2, b equals negative 4, and c equals negative 6. Step 2. We carefully substitute those exact values into the formula. We get x equals the negative of negative 4, plus or minus the square root of negative 4 squared minus 4 times 2 times negative 6, all over 2 times 2. Step 3. We simplify what's under that radical. Negative 4 squared is 16, and negative 4 times 2 times negative 6 is positive 48. So we have the square root of 16 plus 48, which simplifies beautifully to the square root of 64. Finally, step 4. The square root of 64 is 8, so we have 4 plus or minus 8, all divided by 4. If we add, 12 divided by 4 gives us x equals 3. If we subtract, negative 4 divided by 4 gives us x equals negative 1.
Moving right along to section 3, the discriminant tells all, predicting the solutions.
So, a real game changer here is that you don't always have to solve the entire formula to understand the behavior of your equation. There's a specific chunk of the formula under the radical that acts like a crystal ball for predicting your solutions. That expression, b squared minus 4ac, is called the discriminant. By simply looking at its mathematical sign, we can absolutely dictate the nature of our solutions. If the discriminant is positive, the equation has two real solutions. If the discriminant is exactly 0, there is exactly one real solution because adding or subtracting 0 just gives you the same number. And if the discriminant is negative, there are no real solutions at all.
Let's do our second pause check to really lock this in. Go ahead and pause the explainer again. If you're doing the math, you simplify the discriminant and you get -16. How many real solutions does the equation have?
The answer is 0 real solutions. The mathematical reasoning here relies on a hard boundary in the real number system. You literally cannot take the real square root of a negative number. A negative discriminant physically stops us from finding real roots, meaning if we actually graphed it, the parabola would never even touch the x-axis.
Section 4. Checking our solutions. Proving equality.
In advanced mathematics, we hold ourselves to a strict standard called attending to precision. It just isn't enough to find an answer. We need to take the answers we found and prove beyond a shadow of a doubt that they actually work. Let's verify our earlier work. Step 1, we write out the original equation. 2x squared minus 4x minus 6 equals 0. Step 2, we take our found real solution, x equals 3, and plug it back into the equation every single time we see an x. So that's 2 times 3 squared minus 4 times 3 minus 6 equals 0. Step 3, we simplify following the order of operations. 3 squared is 9, times 2 is 18. Then 4 times 3 is 12, so 18 minus 12 minus 6 equals 0. Step 4, we resolve it completely. 18 minus 12 is 6, minus 6 is 0. 0 equals 0. Our algebraic steps are perfectly aligned, and equality is verified. The math holds up for sure.
And finally, Section 5. Which method is best? Recap and transfer. Completing the square requires preserving equality and applying the plus or minus symbol correctly. The quadratic formula solves any ax squared plus bx plus c equation when a does not equal 0. Simplifying the discriminant instantly reveals if you have 2, 1, or no real solutions.
We've covered a ton of ground today, and now it's time to look at the big picture and challenge your newfound decision-making skills. Consider the equation x squared plus 8x plus 15 equals 0. Would you choose to solve this by completing the square or using the quadratic formula? And exactly why does that algebraic choice make the most sense for you?